Hi, and welcome to the eBPF and Cilium Office Hours live stream. I'm Liz Rice. This is episode 91 of eCHO. So welcome to everyone who's been watching since episode 1, and welcome to everyone for whom this is the first time you've joined us. As always, we'd love to hear where you're watching us from. So do say hello in the comments. We already have Sadiq joining us from Oman, joining us from Dubai. So hi to Sadiq. Thank you for joining us. And yeah, do say hello from wherever you're watching in the world. So we're going to be talking about a new feature in Cilium. But before we get to that, I'm going to just run through a few headlines. So as always, the show notes are available on HackMD. You can find them under the eCHO Live that corner. That corner is the link. You'd think after 91 episodes, I'd know which corner those were in. Okay, we also have Russell joining us. Hello. And Edward joining us from Russia. Thank you for joining us. So, as always, there is a Cilium newsletter that our colleague Bill Mulligan puts together. You can find that from cilium.io/newsletter. I found three articles that kind of piqued my interest in this edition of the newsletter. The first is NetReap, which Cosmonic have recently open sourced, and it's an operator for running Cilium in Nomad. So for those workloads that don't necessarily suit running under Kubernetes, Cosmonic have shown how to use Cilium in a different orchestration environment, i.e. Nomad. So it's great to see that that's been released, and I'm hoping we can line up a guest to come and show us that in practice. That would be great, I think, for a future eCHO. The next article that I wanted to highlight is an updated version of a now fairly, well-established article by Paul Chagnon, talking about the complexity of the BPF verifier. And it's pretty interesting. He's been keeping this updated over time as the verifier has matured and as new features have been added into the verifier. So yeah, check that out if you're interested in seeing how complex the verifier really is getting these days. And then finally, I liked the look of this article, which is an introduction to using the Cilium eBPF Go library. So there's some background here. And then if I scroll down a little bit further, there's some talk about installing Cilium. So it gives you a little example about installing Cilium. But I also particularly liked the fact that this article is showing us some examples of using the Cilium eBPF Go library. So if you're interested in eBPF programming, you might find something like this an interesting way to get started if you're a Go programmer. Okay, and before we go on to the main topic, just going to say one more hello to Kartikeya joining us from India. So welcome and thanks for saying hello. And now, without further ado, I think we should move to our main topic for today. Let's introduce Dylan Reimerink. So hi, Dylan.
Hi, Liz.
And we're going to be talking about a new feature that's been added to Cilium, which I think it's fair to say the naming of this is a little bit not completely settled, but it's about announcing or making services reachable, announcing them through ARP, although announcing maybe isn't the right term. We'll come to that. But basically, layer 2 visibility of service IP addresses. Is that about the reasonable summary of it?
That's a reasonable summary. Yeah, really excited to show this off. It's been in the works for a few months now, and we're finally at the stage that it's currently in review. So hopefully soon makes it into the main branch of Cilium.
Fantastic. So I called it originally, when I titled this episode, I called it Layer 2 Aware Load Balancing. And then I ended up thinking load balancing doesn't sound quite right to me, more service announcements, something like that. But before we get into exactly what's happening here, should we just set the scene and just talk about what we mean when we're talking about Layer 2?
Yeah, that sounds about right. So you want me to do the honors?
Yeah, go ahead.
Yeah. So well, when we're talking about layers, for those not in the know, we're talking about the OSI model, which describes these layers of the internet. So commonly you will hear layer 2, layer 3, layer 4, and layer 7, which are all of these interesting parts where we either have TCP or actual IP traffic. And what we'll hit today is the focus on layer 2, which is typically it's Ethernet. So it can be a lot of other things, fiber channel and other such things, but in most cases we're talking about Ethernet. So switched networks, computers that are typically all physically or physically connected to some sort of shared switch and so on. And the interesting so normally when we think about Kubernetes, we are thinking about the cloud, so AWS or in the Google Cloud somewhere, where you normally don't deal with layer 2 directly. That's all done by the cloud provider. But there's a growing interest in on-premise deployments being either bare metal or in some sort of VM environment, and that's where features like L2 announcements, L2-Aware, LB are really going to shine.
I think another way of thinking about the layers is to think about what the addresses are. So, layer 3 is IP addresses, layer 4 is ports that you might be using at a particular IP address, and layer 2 is MAC addresses typically, right?
Yeah, right.
Right. Okay, so I'm wondering if the next thing we should do is move to showing it, because I think maybe showing it is going to be as easy as describing it. Shall I?
Yeah.
Yeah.
I think it is, and then we can do some commentary along the way.
Yeah.
So what we have here is an Instruct lab, which some of you are hopefully familiar with. Most of you are hopefully familiar with. And this particular lab was created to demonstrate this new feature. So what we have is we have quite a simple cluster. We have a kind cluster configured with a single control plane node and 2 workers. Cilium is installed on here with some new settings. So let's first of all check that everything works, and it seems to. And in particular, if we ask it for the current configuration, you'll see that that there's a new option in this particular version to enable L2 announcements and some configurations around that, which we'll get to a little bit later.
Can you try making the font a little bit bigger? I think it might be, if it's possible. That looks better.
So.
Yeah, that's great.
This is better? Yeah. All right.
Yeah.
So what is a bit in this case we have our main nodes, and they are connected via an additional network interface. So all of our nodes, I'll see if I can actually show that. So we have our nodes, and I probably need to enter a pod somewhere. So we have all of these nodes. They're running our Cilium infrastructure. But of course, we have to type out our whole string to get in there to show you this. But now that we are in here, I can show you that there are a few links. So we have all of our pods. But what I like to show you is that we have this net zero interface here, and this is what we'll use. So we have connected all of our nodes in this virtual on this net zero network. Which are all connected on a switching level. So it is as if all of these nodes, while they normally are connected, we connected these three nodes, and we have given this particular network interface the 12 prefix. So these can all reach each other on the same link level network, and then we have one additional node there to show you what happens when you add non-Kubernetes devices on this same network. Does that make sense?
Would this be as if you had an Ethernet switch and each of your Kubernetes nodes were connected? They were, had a wire connection into that Ethernet switch, and then there's also some other workloads that aren't Kubernetes but are also plugged into the same switch.
Yeah, that's exactly what this is.
Great.
So the first thing so we have this. I'm going a little bit out of order in the labs here. But what I'm going to do is I'm going to deploy a workload. So I have this service workload, and if we actually go look into it, then it's quite simple. So we have this service which we'll call DevStar. It's just a normal HTTP service, but we did configure a specific external IP on there. So we have an additional external IP, and that's within this range of this net zero subnet that we had configured. We have our deployment, which are just two pods that echo back, so we have something to look at, and they should be up and running now. Yeah. So if we can look at the service as well. We can look at the services as this external IP. So everything looks correct. So what we do then is to be certain, I'm saving this IP address right now in this terminal, and then we can try to access it. So like I said, we have this neighbor that's configured on the same network. So if I go here, it is the .1 on the same network, and it also has this net zero. This net zero device, and then so if we attempt to connect to this IP, we'll try, but it doesn't work. Well, we get a connection timeout after 1 second. It doesn't. So your typical flow doesn't work, even though we configure the IP. Nothing works. And if you wait a little longer, we'll get a no route to host error. But I know that it's there, it's configured. So why doesn't it work? And the reason for that is because this virtual IP isn't actually assigned to any node. So there's not an actual Linux instance that recognizes this IP address and responds to it. And that is really what this feature is all about. So we can artificially assign this virtual IP to one of the nodes in our cluster, and then respond to it to attract traffic to a certain node, which then will act as a load balancer within the cluster. So we use. So
if we thought about this at the kind of layer 2 level, what's happening here is that neighbor that's outside of the Kubernetes cluster is basically it's sending out ART requests saying, tell me where 12.0.0.100 is, and there is nothing that knows where that is right now.
Exactly. So we can do an ARPing and we just get a timeout. So we send out ARP broadcasts, and there's nothing currently that responds to these broadcasts. It's all being ignored because everyone on the network thinks, "Oh, that's not me." The way the way this works is we have to enable the feature to begin with. And after that, we can manage the specifics with policies. So I have I have an example policy here. Let's call it policy 1. It will respond to external IPs and also load balancer IPs, which typically don't work in local environments. We have a list of interfaces here, so I just say, okay, which actually is a regular expression. So you can select multiple interfaces, or you can leave it blank and then it will respond to all interfaces. So you can pick on which interface do I actually want to respond, or do I want to respond everywhere. Can select our services, and in this case, I've excluded the control plane. So we will only ever schedule this virtual IP on one of the worker nodes. The reason for that will become apparent in a moment. So let's apply it. Let's apply this service. And the one tricky bit here is, which is part of the lab, but which I don't care that much about right now, is that there's a label mismatch initially. So our Dev Star service was originally red, now it's blue, so it matches our policy. Now that we've done that, our policy is in place. We have our services. So if I now attempt to curl again, we get a response. Magic. So, well, of course it's not, but if we now do the ARPing, we can see that there's actually this MAC address, or we now get a response saying, okay, you can reach this IP address on this specific MAC address.
And is that MAC address, I mean, it's not a real physical interface. Is it a virtual? I guess it's a virtual interface.
It's a virtual interface. So this all happens within a virtual machine in the cloud somewhere.
Yeah.
But this MAC address is actually, so if I were to look here, so this virtual machine or this node has a MAC address. It's not the same, as you can see. But this is actually the MAC address of one of the worker nodes. I don't know which yet. We can kubectl. So we can take a quick peek. So it's currently worker 2. So I would expect that if I would do the same trick of entering a pod, and I pick the pod that's on worker 2. Let's see which one.
You might need
which one that is. Yep, I need to wide.
Wide, yeah.
So it's not very easy to spot. Worker 2 is this one. Now let's hope that I'm not a liar. So when we enter this and we go look at the links, then net 0 is F4A9, and that is exactly what we see here.
Yeah.
So it responds now. It now responds back with the MAC address of the link over which it is reachable. So if we were on a different, so if we were connected over the East 0, for example, then it would respond with a different address. So it depends on where you actually on which interface you actually ARP. That's where the MAC address comes from. Yep.
Right.
So that's the basic feature right there. Now now you can ask, for example, why why do you need this? Why would anyone want this? And that's actually the like I alluded to before, you can there's way more on-premise, way more things happen on-premise these days. So it's nice to have a Kubernetes native like way to actually expose additional IPs and stuff like that in the cluster. And this meshes really well together with other features of Cilium, like the policies and service load balancing and stuff like that. It's just a way to really get that external traffic into the cluster.
Yeah, I think we have lots of Cilium users who are they've got both Kubernetes and non-Kubernetes workloads, and some of them have been connecting those different environments using BGP.
Yeah.
And that's, I guess, pretty common in a large environment. But if you have like a home lab or something, you probably don't run a BGP network. I know some people do, but most people
yes,
more likely to just have things plugged into an Ethernet switch, right?
Right. Yeah. Some people do, and we had the BGP. So in 1.13 we introduced service load balancing with service announcement via BGP on our new control plane. And that has worked. That basically fulfills the same role, but that's what we would call L3, because that happens at a routing level, and this is a translation between L2 and L3. The nodes want to know where to send traffic, and then we tell it which layer 2 address they can find the service at.
Right.
And BGP is quite a hard thing to do right, and not everyone wants to. And it's like most common, like everyone's home network doesn't is most likely not BGP routed. It's just your local router with configured somewhere. Or if you're a bigger company, you probably have a few subnets and they're all linked together via firewall, but you don't actually have BGP everywhere. So in those environments, this is really valuable feature to very seamlessly integrate a Kubernetes in the rest of your network.
And presumably that external service that wants or external client, let's say, that wants to reach that Kubernetes service, it's still got to find out what that IP address is somehow.
Sorry, can you say again?
So in this case, we had the Death Star service that's being advertised. Well, not advertised. It lives on, I think it was 12.0.0.100, and you would need to know that your external client would need to know that IP address.
Yeah, exactly. Yeah. So there's this. In this case, we configured this specific external IP address. And you can use DNS or something else to link that, of course, even internally. But before, if you didn't have the ability to announce this in this case, we chose this IP address because it matches with our the setup. But if you didn't have this, you would have to use something like a node port service to get that traffic in your cluster. And that's problematic for a few reasons, because node ports typically can't, or I believe you can configure it, but out of the box they can't use privileged IP address privileged ports. So you can't actually use port 80 or 443 on your node port. All of your services share the same IPs, so you can't do IP based whitelisting, so you can't just block a whole IP or specific ranges, and of course it's not highly available. So if you had a node, if you had a cluster with five nodes, for example, you say, okay, I pick node 2 to be my north-south node, and that's the IP address that I always use in the rest of my infrastructure, and that node happens to go down. then technically on one of the other IPs of the cluster, you can still reach the service, but your clients don't know that. So they either need to implement some sort of client-side load balancing, and that's difficult and not standard. But what the cool thing is about this feature is that it has failover. So I'll go to the next step in this lab to demonstrate it actually.
While that's loading up, I'm just going to say we've got some conflicting opinions about BGP here from the audience. So Russell says, my rule is if I can avoid BGP, I avoid it. And Tony, hello Tony, says he thought BGP was second to DNS in everyone's home.
I'd like to see that day.
Yeah, right after this show, I'll go and set up some BGP in my network.
All right. So I can actually I can demonstrate that. So going back to our nice ARPing, I'll just open this and keep it open in Terminal 2. And what we're now going to do is we're going to actually kill off one of our nodes. So
we're going to kill the one that is currently responding to those ARP requests, right?
Exactly. So this is one also partially a limitation. Is that ARP, because the way ARP works is that you have this nice ARP table where it's just a one-to-one conversion from IP to MAC address. But it also means that that only one node in a network should ever have a response to these ARP requests. If you have two at the same time, you get very strange networking issues. So in the background, we actually have to pick one node. We pick it mostly at random. And in this case, it's worker 2, and we use the Kubernetes leases system to make sure to actually do the health checking. So Kubernetes already has this very nice high availability system in there, and we basically use the API server as an authority, and every node periodically checks if it can take this lease, if it's available or not. And it will detect. So if you look here, you can see when the lease was actually acquired and the last time it was renewed. So this time will actually change and update constantly. And we also say that if this lease hasn't been renewed for 3 seconds, then someone else should take it over. So then someone else should take charge of it. So what we're going to do is we're going to kill worker 2, and this is also the reason that we didn't want our control plane to be one of the leaseholders, because we currently don't have a highly available control plane configured in this cluster. So that would give us trouble. So these pre-prepared commands do a few things. So we're going to look up the MAC address. We're going to find which virtual interface this is, and we're going to kill it. And the reason we're doing it in a slightly complicated way is because to actually simulate down like unplugging a cable, we have to both kill kill our host, but all via Docker, but also remove its physical remove its connection from this virtual switch, so it actually doesn't respond anymore, because otherwise it will still continue for a while. So if we go back, I've everything prepared. So we currently still have the MAC address of our old node, but when I actually go and kill it, we'll see that we time out for 3 seconds, which was configured, and after those 3 seconds, we detect that our old node has gone down, and our new worker takes over. So if we now go look at our lease again, we should. Where is the? We can say that it's now just worker 1 and not worker 2, and our lease has an increased transition, so it moved from one worker to the other. So that's failover for you. So and if I now were to send a curl request, then it still works. It's just that we will send this traffic to a different node on the same layer 2 network.
Brilliant.
So it's almost magic.
I'm sure it's not magic, but I'm sure it is eBPF. So I wonder if you can tell us a little bit about how it's implemented. I mean, is it as simple as an eBPF program that's attached to an interface and is responding to ART requests? Like, there's probably a little bit more to it than that, but
yeah. It essentially is. I can dive a little bit into that. So we have a few programs that we always use for Cilium. One of them is the NetDev program. And the NetDev program usually does, is actually responsible normally for load balancing node port requests and some early firewalling and encapsulation stuff. So it lives on every actual network interface that's external. We attach it to be able to do a number of things.
Is that attached to XDP or somewhere else in the stack?
I believe it's normally on TC, connected to TC, but I believe it can switch actually. So it can, depending on a few things, it can actually either run in XDP or in TC, if I'm not mistaken. But I think I'll be corrected if I am. So I have to retype this thing to get into. This is always the most fun part about Kubernetes, getting into the actual thing. So I now entered the worker, so the Cilium worker node. And if perhaps I can show you. So we have this net zero interface, and on this net zero interface, there's a queue, like a TC queue disk configured currently, and it's on there. And I'm not even going to attempt to try to. There is a way I can show you the actual program that's attached there, but for now you'll just have to believe me. So what I can show you is that once this program is attached, we have to still tell it when to do certain things. So
I think it's map list.
Yeah. So in this case, the interesting thing is that we're sharing a kernel here. Because we're on this single environment. So I actually have to check all of them. So these are our three or like all of our eBPF programs for the 3 nodes all coexist in the same kernel at the moment. So I believe I can dump the map contents like so. Yeah, so this one is empty. 6, and this is the one. This is the map we're currently at. So what is actually then? So our agent manages the contents of this, and you'll see. And in this case, what it does is it says, okay. Or actually, sorry, I think I'm mistaken. This one is the killed off node. This is the reason. So because we killed our node very abruptly, it didn't have it didn't clean up the map.
Okay.
This was our old one, and this is the new one, but you can still see it's the same IP address that's configured on there, and there's also the interface number, and this interface number lines up with our net zero interface that we have here. So that's the way we tell eBPF to start responding, and then it should actually increase this value here. So if I start the rping again, can I quickly get that command back? we should see this number increase over here. Yeah, so you can see that the number of responses increases. So this is the only instruction we give it. So we tell it, okay, you can, if you see requests for this IP on this network interface, then you can respond with the MAC address of that interface. And this map contents get resolved based on everything that happens, but also based on your lease. So if we I can't demo that right now because we killed off this older node, so I can't show you what happens if you were to delete this lease. But it basically, normally it switches between nodes if that happens, and then these entries actually get nicely removed instead of this case. So so I showed you that the lease duration by default is by default it's 15 seconds. In this case, we already configured it to be somewhat lean, but because there's this trade-off, right? If you have very fast lease, if you have a very fast failover, then there's a lot of health checking communication that has to go on, and if you don't care that much, just that it recovers within a sort of reasonable time, then you can get this make this a little bit longer and save some network and CPU overhead. But it all depends on how much you want to what is important for you. So these are the Helm Helm values that I also showed you at the very start. So the lease duration is the period after which we fail over. This renew deadline is the interval at which this value is the leaseholder value is renewed, and the last one has to do with retries if the API server is temporarily unavailable.
Right.
So in this case, we would say worst case, it would take 4 seconds before a node discovers that something is down, and best case, it's right after that 3-second timeout that something fails over. And this is all up to the users, of course.
So Will's asking, so I think this is sort of clarifying his understanding of what's happening. The Cilium agent tells the eBPF program to start believing that it is a certain IP address, which will allow or rewrite incoming packet IP addresses so that the interface will respond. I think it's more just the ARP request.
Yeah, it just responds to the ARP requests. So normally all ARP requests are getting forwarded to the network stack, the Linux network stack. But the Linux network stack would only respond to those IP addresses if it was actually configured on an interface somewhere. But these are floating virtual IP addresses, so they are never actually installed anywhere on an actual network card or whatever. So typically nothing responds to these. So the client never gets a response, so it would never actually send an IP packet. And once we start responding, that's the moment the client actually starts sending the IP packets, and the rest is already taken care of by existing Cilium features. So the moment we configure this service, let's see. So we have the service right here, and the moment we configured it, we already made Cilium ready to accept this traffic for this IP address. And then internally we can still do, so if you have 20 pods, then we still do service load balancing. So the traffic to this service gets load balanced over all of these pods. But
right. So it might actually end up at a different node from the one that's advertising or responding to the ARP requests, because it might be load balanced to a different pod.
Essentially, the node that is picked as the lease holder is acting as sort of your north-south load balancer at that
Mm.
point.
Mm.
Um,
So Will had a couple of follow-on comments. So he's saying, so we start responding with the local ARP address when we want to take control. I think, yeah, when we want to say, yeah, we know about that IP address. So yeah, we want to start, we know how to, receive requests to that IP address. But then an interesting follow-on question from Will. If there's a host with an ARP cache, could we have a delay in failover?
There is. So what we also do, or technically it's planned in the current PR, but what this feature is going to do in the like in the actual release of Cilium, is that when this failover happens, we will send out what's called a gratuitous ARP reply. So we'll actually broadcast an ARP reply saying, "Hey, this is the new MAC address of this server of this IP address." So all of the nodes know that they or can change their ARP cache entry. The caveat is that nowadays, because that's of course can also be used for nefarious purposes, that not every node accepts these.
ARP spoofing, yes. I
Yes.
remember doing it's a bit of a distant memory, but I remember doing a pretty fun demo of a vulnerability in Kubernetes with ARP spoofing. So
I believe the famous tool was Kane enable or something like that to actually do spoofing, and yeah. But so due to that, not everyone accepts it. But if you do trust the nodes in your local cluster, you can enable it, and then your even nodes with an ARP cache should have this immediate failover due to the gratuitous ARP. But that's a very, very good question, actually.
So Will also said, thank you, nice, great solution. Thank you, Will, for the questions. That's really good questions. If anybody out there has more questions, do type them in. We love having questions. That's always great to hear from you and make sure that what we're saying makes sense. I guess another question for you, Dylan. Everything we've seen here so far is IPv4. Is there a V6 equivalent?
There is a V6 equivalent. So instead of ARP, you would use it's technically ICMP V6, but and on top of that, there's this protocol called Neighbor Discovery Protocol, which basically functions the same way. But unfortunately, this first iteration of the feature doesn't have support yet. That is really baked into the design. So in a future iteration, we certainly plan on adding support. But this in this first PR that we're currently merging, it's not yet there. But yeah, that's certainly on the roadmap because I believe I can confidently say that we as Cilium firmly believe in an IPv6 future. So that's certainly something
when Cilium was very first created, it was actually IPv6 only initially. So
yeah.
although back then that was a little bit ahead of its time.
Exactly. Yeah. So yeah, it's not there. So yeah, it's not there yet. But I certainly expect it to be there in the near future.
Great. Anything else that we haven't talked about that we should have covered talking about this feature?
I think the last thing that is mostly part of this lab environment, which perhaps is really cool to show very quickly, is that this works together with other existing features. So the Cilium load balancer IP pool, for example, which we added not too long ago. So this is basically IP address management for load balance services. And this is advantageous because so far we have worked with these hard-coded external IPs, but you might not want to hard-code IPs all the time, or you want to make things more easy. Then you can make this automatic. So we are just saying, okay, we're making this CIDR of IP addresses available, which is again within the same range we have been working in so far. And if I now make this new deployment where we use a load balancer type, even though there's no load balancer in here configured because it's on premise, we're not on a cloud. The moment I make all of the labels match, we get assigned this external IP address. And this external IP address is then also immediately, sorry. Uh-oh.
Okay, so, live demo time.
Live demo time, yes. So this IP address should be, perhaps it takes a while. Now we have something interesting. So this external IP address should also be announced right now. I think it's maybe because we killed something off or did something wrong with regards to the labels. So normally this should do its thing. Let's see if it actually responds to ARP or not. Actually, I'm also going to pick up this IP address to make sure. I think I did something. It does respond to ARP, so it does work. I think I did something wrong with the macros variables here. Yeah.
Yes.
So it does. Yeah. It does work.
So yeah. Demo Jeopardy. It's always good.
Yeah. So this is basically the last thing I wanted to show. So it works with load balancer IPs and external IPs, and the load balancer, like our existing LB IPAM mechanism, is really powerful way to manage things and to, for example, give certain namespaces, certain IP ranges, etc. to really go the full mile. Yeah, that's. I think that concludes what I have to show you today.
Brilliant. Thank you so much for showing that. Russell made the comment that IPv6 is 27 years old, which is exactly my age. No, it's not. Yeah. So yeah, it's been taking a while for us to ramp up into the world of IPv6, but I guess we all came up with other solutions like NAT. So yeah. Yeah, I think that was brilliant. Thank you so much for showing us the demos there. And I guess we can expect this to be part of the next Cilium 1.14 release.
This should be in 1.14. Yeah.
Yeah. Great. Thank you so much to everyone who joined us, for saying hello, for sending your questions in. It's always great to get live questions. And yeah, we'll see you next week, or I think Duffy will likely be back as host next week. Have a wonderful weekend, and thank you to Dylan.
Thank you for having me.